Hi, I'm Kevin Reynolds, and this is Screencast assignment number 3, where we're going to look at cooperativity. Now, when looking at this, there's a couple of things that play a role. One of the big things is going to be our type of cooperativity. In this, we have 3 different types. We have positive, negative, and non-cooperative. We're going to focus on 2 key ones in this kind of presentation, which are going to be our positive and non-cooperative. Now, there's a couple of factors that play a role when we look at these. Some of these factors or parameters that we kind of see when we're diving into this are things like our ligand concentration in regards to a protein, the different rates that we can possess, and the fact that you can have multiple binding sites on one protein. For the sake of this, we're going to be looking at 2 binding sites. Now on this far left molecule you see kind of over here as protein necessarily, we have 2 binding sites. So our top reaction is what we're going to be looking at as our positive reaction or positive cooperativity, where K1 is the rate of the first ligand binding to the first site right here, and then K2 in red will be the second binding site, which shows up right over here. The bottom of it with the K1 and K2 in white are just the negative cooperativity. We're not necessarily going to get into that. We're going to start off by looking at a non-cooperative thing. We're going to look at it in 2 different ways. We're going to look at linear and nonlinear. So what we're going to move to first is going to be the linear relationship of our non-cooperative. You'll kind of notice that it's a negative regression or a negative relationship between the total bound and the amount bound divided by the ligand. This is kind of in reference to the fact that we're going to be looking at a dissociation or a KD of it, as our KA in a sense, when we get to the nonlinear, shows up in a kind of weird way. So moving down to there to explain that a little bit further, we're going to look at this point right about here, which is the halfway saturation point, so the half bound. At this point, your KD is equal to your 1 over your KA, or your inverse KA. So this is kind of why we're looking at KD more so than KA, because we're looking at this dissociation of the ligand from the actual binded site. So you'll kind of notice in this that it holds this hyperbolic kind of trend, which is kind of going to be really nice and whatnot to look at in relation to our positive cooperativity. So looking at this positive cooperativity, we're going to go back down to our linear relationship, which we see here in red. Now transpose it over the non-cooperative just to kind of show that it's not necessarily linear. But what it's kind of getting at is that in positive cooperativity, when you bind to the first binding site, it's going to increase the rate for the next one, which is why we see this concave down, kind of really sharp increase in rate. Moving down to the nonlinear, it's kind of a little bit different. We see the sigmoidal kind of aspect, which is representative of the same similar concept, that there's this increased rate. Moving a little bit more in depth in it, what I did is transposed our nonlinear ones, and this dotted line is kind of what the negative would kind of show up as, our negative cooperativity. So what it's kind of getting at showing is that in both cases of cooperative and non-cooperative, you have this increased rate, whereas in negative cooperativity, you don't necessarily make it to this plateau peak where each of the other 2 are going to receive at.